All right, welcome to the next lecture, the next week. So this week we're going to talk about quite a few things in this set of slides, and eventually we'll get to that midterm review. But the first thing that I want to talk about is templates. And if you are potentially coming from Java and you have seen something like this before, the Java term for this is generics, aka generics. Boop. Okay, back to a normal color. So let's set the scene. Pretend you wanted to make a maximum function for ints, and you know how to do that. Be like, I don't know, it's called maximum. It takes your two ints that you want to take the maximum of, I don't know, x and y, a and b, whatever you want to call them, and it returns which one was bigger, right? Returns back the max. And so you'd be like, I don't know, if x is greater than y, return x, otherwise return y, standard stuff. So that's a horrible brace. Let us make it beautiful. Third time is the charm. Good enough. Okay, so pretend we have this, and it's all well and good. We have a maximum function for ints. Now suppose your program has, I don't know, 100 million types, and you need a maximum for each of them. Okay, you got your do types, your boo types, your poo types, all of these things, and the maximum function is the same because they all have those tiny little, they have the greater than operator that works for them. You just have to go and re-implement the same function 1,000,000 times, 100 million times to be precise. That's no fun. We don't like this. How can we solve this problem? And the answer is using this thing called a template. So instead of this mess, let's write one maximum function, okay? Let's write just one maximum function. And have it work for every type. And in essence, we're not just writing one, we're writing one that can become many different types. We're writing a template function that will be filled in with the appropriate types later. And this will all make sense when I give the example. So this is what we have. Let's make this happen. So the way that you do this is, let's just go to code, I think. Boop. It is lecture 11. Welcome. Let's say vim max. I don't know. How about that? Okay, here is our one max function. So it's called maximum, I guess, still, but what it takes is something different. It takes an x and a y, but the types are going to be weird. Okay, they're going to be any possible type under the sun. And the body is going to always be the same. We notice that it will always be the same, no matter the types, so long as they have a greater than operation implemented on them. If x is greater than y, return x, else return y. But what are these types? If we wanted this to be templated, it could be any type. And that's the point. Let's make it a variable type. Whatever it is, call it t. Okay? And what it returns, what type does it return if we're using this variable type called t? It returns a t. Do you see this? Okay, so we're going to make up a variable type name. And call it t. Okay? And I guess this is the key here, so let's make it bold. And the way that we say that this is a variable type, we have to say some fancy magic words, otherwise C++ is going to be like, I don't know what you're talking about, there is no type called t. You have to say we want this to be a variable type. So we'll say template, and be like type name or class. I think it's a bit more cool these days to say class T, so I'm going to teach it like this. All right, so this is the one extra magic line that you need to say, hey, declare this line declares a template variable called T that could stand for any type. And let's see, I always get in trouble with this, so let's put it here. Okay, so with this line, it's like, okay, imagine that there is a class T somewhere, or just a normal type T, doesn't matter. And now this maximum function works for any T, x, ty, and it returns a T. So you can fill this in with whatever we want. We could fill it in with int, we could fill it in with boo, with poo, whatever you want. And you've seen this already. You've seen this notation. You've used vectors. You've used lists. They are all templates. So here's how you can use it. And I'll show you a couple ways. So let's see out the maximum of, I don't know, 42 and 43. We know what it should be. And this is the maximum for ints. Do you see that? Isn't that nice? Dun dun dun. Oh, and I just spelled it wrong. Sorry about that. We're using the maximum function, and we're going to replace, it's kind of like you're calling it with arguments up here, T with int. Okay? You can call your function with a type argument. Isn't that interesting? So now you have type arguments and you have normal arguments. All right, so maximum of ints. Maximum of strings, perhaps. I don't know. Poo. Poo. Now let's put poo first because we don't know if it's going to work properly otherwise. Okay. And we'll just include string. Maximum of strings, please. And let's get this all to work. And let's show you it running. Here we go, here we go. Hey, it's so nice. So one function can become many different functions. You can call it with a type argument. You see that? It's beautiful. Let's see, what else do I want to do here? One thing that you can do is replace T with int. Replace T with string. C++ is actually smart enough to figure it out. So you don't have to do it. You don't have to use the angle brackets in this case. So you can do the following. You don't have to say double, you can just say 3.14, 5.67, or 4.67, whatever. Okay, and it'll figure out the types for you. So it's like, what could T be? I got a double here, and I got a double here. I'm pretty sure he meant double. And it'll just work. So technically I could get rid of this, and get rid of this, but this is always correct. It's just giving extra information in this case. Alright, so this is you've seen this notation before. We're just rolling our own at this point. We did this ourselves. It's happening. Okay. Another example. Doubling numbers or strings with the same function. And I'll probably just keep it here. Why not? So I'm going to make a double function that does the following. Alright. Call it double. It's going to take some t called x, and it's going to return x plus x. Okay, so anything that has a plus operator on it, it'll return that thing back doubled. And there it goes. Oh, I can't use this word, double. What should I call this? Dub, perhaps? And now I can use it on strings and numbers, like cout double, dub 42, cout dub hello. Isn't that so cool? It'll work on both types. Dun dun dun. Oh. One thing I'm gonna have to do is make sure that this is a string. Otherwise it's not gonna work. Don't mind me. Hey. So it's using the plus operator on ints and the plus operator on strings with the same function, specialized to a different type. Isn't that beautiful? Alright. We can go further. Let's make a templated class now, because we have noticed, we've seen that it's possible to have classes that don't really need to care about the data type that is inside of them. For example, lists and vectors. It's just hold an array of stuff, hold a bunch of nodes of a certain kind of data. We don't have to deal with what's inside right now. We can just get it out. And so let's make a simple class. Let's call it adder, and let's make this work. All right. So I'm going to make one big file at the moment. So let's call it, I don't know, useadder.cpp for now. Yeah. So I'm going to make a class. I'm going to call it adder. And it's going to add two things of a certain type. I know, very contrived, but it's going to be okay. So it's going to take two things to add. tx, ty, and we're going to add those things. So adder, let's have it take, I don't know, the x and the y, and then we'll initialize it, and then we'll have an add function that just returns the sum. Okay, so this constructor, and this is return the sum of x and y. So hopefully this all makes sense. Just replace t with your favorite type as an example. It'd be like int, bool, string, anything that can be added. Alright, so now we have to say to the entire class now that everything inside of here has a variable type inside of it. Alright, where we have a t. So we say template class t, and then the entire class adder. Okay? And then we can go and define all these functions as we normally would. We can say, I don't know, adder, tx, ty, give it some implementations, same with add and all this. It's adder's add function, give it an implementation. But again, we have to say templates again because it's a function, okay? So we have to say, even though we set it up here already, we have to say template again, okay? Every time we define a function outside of the class, even if it's a templated one. A template, for using t's, it has to know about those t's. And of course you can call t whatever you want. P, q, anything, even a normal variable name. Class t, and then it will work. But there's one more key ingredient. It's not adder anymore. It's a special kind of adder, just like you say. Vector int, vector bool, things like that. The name of the class is no longer adder. It's adder t. A different class, essentially. for each type you use. So the reason that it does this is because it's going to eventually need to make all these different functions for you to use. It'll just do it under the hood. So there's always a specific name for our class. Okay, so it's not adder anymore, it's adder t, just like it could be vector t, things like that. Adder t. Okay. And let's go and implement this now. Well, this only needs an initializer list, so let's do that. It'll be like x is x, y is y. And this thing needs to return something, needs to return x plus y. Okay. Extra qualification on member add. Let's see here. Oh, I forgot the template class again. That'll do it. Okie dokie. Now we can go and use this class in many different ways. So we can make an adder of ints, an adder of strings, as normal. Okay, maybe I'll include strings, just so we can do that. Alright, so let's do this in main. Let's be like, hello, I would like to add 2 ints and then 2 strings, using 2 separate adders. Okay, so how do we want to do this? Let's say adder, int adder, we'll give it 42 and 43. Then I'll make a string adder as well. But again, we have to say the template arguments. It's not an adder anymore, just like it's not a vector by itself. You have to say vector int, vector string. Alright, so it's an adder of ints. It's an adder of strings. Okay. Hopefully that works, and obviously this needs some strings inside of it. Let's give it a string hello. And, well actually, because I gave the templates, I don't have to convert like that. I think. Hello, or hi space, mom. I think that'll work. Yeah. Okay, so now we can run their add functions. Cout int adder dot add, and that'll return t, which in this case was an int, and it'll add those 2 ints. And in this case, if I say string adder dot add, it will add the 2 strings. Isn't that cute? Alright, so let's watch this work. And I guess I'll try to get the class definition in view, but really, this is all that really matters, the implementations. Alright, so an adder has 2 t's inside of it, called x and y. It can be whatever type you need. And you can get those in with the constructor, and go and add them with the .add function, or the .add method. Okay, so let's watch this work. Oops. Okay. And so it's going to add those 2 things. It's going to add the ints, and it's going to add the strings. Isn't that beautiful? Alright, so those are templates in a nutshell. And now you can do whatever you want with them. And you can use this type however you need to. You can be like, it's going to take a pointer to a t. It's going to take a constant reference to a t. Things like that. That is not an issue. Here, everything's passed by value. Okay, so what I do want to do now is split it up into a .cpp file and a library. We've got our use adder.cpp, but I'm going to put my adder in adder.h. Yeah, go back. And I'm going to show you the one weird thing about templates. So, the one weird thing about templates is that you can't separate the class definition from the implementation. Everything below needs to get included for templates to work. Okay? Okay. Which is an odd thing, but it's just that you can't separate these. You can't put what I've highlighted, the implementations, into an adder.cpp file when you're using templates. You can, assuming you include that file right here to copy and paste it, if you wanted to do that, but it's not really necessary. All right. So that's there, and let's go and include it now, of course. And it'll work as normal. And we only need to compile, remember, use adder.cpp, because this is a header file. It's getting copied and pasted. We're going to have to separately compile that. It's possible to do it, though. You can compile headers if you wanted to. But it's unnecessary. So it's going to work just fine. But the one weird thing you need to remember with templates is you can't separate the definition from the implementation. It all has to be included, okay, for these things to work. And that's a good segue. Why in the world is that true? Why does that need to be the case? Okay, why can't you separate the code and compile it separately? And the reason is the way that templates get translated into code. So a template, class, or function is not actual code yet, okay? That is the weirdest concept. You can't just say, I don't know, you can't just say template class t maximum and then never use it anywhere and expect a maximum function to exist in your program. That is not what's going to happen. It's very odd, but I will make it make sense, hopefully. It's not actual code yet. It needs to get translated into its special version. A template gets translated into code, and it gets specialized for each type. And that is specialized for a particular type only when it's used. So, for example, before I ever call, or if I didn't call the template maximum function, it would never get, it wouldn't exist. Because only the second when I use it, only when I actually use that function on ints, does maximum int, does that function get made. Okay, so it's making a bunch of little copies every time you use the actual templated function or the templated class. So, under the hood, C++ is essentially copying and pasting the code and replacing it with the correct types. So in a sense, you really do end up getting, if you end up using your maximum function on 100 million different types, you do really end up getting 100 million different maximum functions. They're just made for you. Okay? Okay. Hopefully that long explanation made enough sense. So if I go back to adder now, hopefully it makes sense. The fact that none of this is code yet is the reason why I cannot compile this separately. If I try and compile this separately, well, there's no use. There's no use of this class. So it's going to be like, I have nothing to compile. Okay? And that's why it's going to get confused. But the second I use the adder class in whatever file I included it from, it'll be like, you use the adder of ints. I'm going to copy and paste all of this and replace t with int for you. Okay? And that's what it's going to do. So what it's going to do here, it's going to make a special separate copy of adders for ints, and then it's going to make a special separate copy of adders for strings. All right. Hopefully that makes enough sense. And now I think you have everything that you need. Let's confirm this is still going. I think you have everything that you need to go and write anything. Templated class, templated function. You can roll your own templated lists now, for example. Let's see how the STL does it. And I think I'm on the wrong page. I'm on stacks. I'm a little ahead of the game. That's a container. It's we still have list. There it is. So you can see class list. Look at that. We know this. We know the syntax now. You can have multiple template parameters. This one has a default value. You don't have to worry about in this class. But it's like template class T. So it's a list that is generic in some type T of its data. And it's called list. That's how it's declared. Oh man, isn't that cute? And then it redefines. It like makes a copy of T and it calls it value type. We don't have to worry about that, but that's what happens when you use it. So it'd be like, what's in the front? Oh gosh. What is reference? It's a reference to the value type. So it's, if it was int, it's a reference to an int. Things like that. And so that's how you can read this kind of stuff. And push back. What does it take? Oh, it takes whatever T was, because they renamed it to value type, apparently. Okay? Yeah. If you ever want to give a different name for a certain type, like what it's doing here, to create an alias for a type name, you can say type def new name equals old name. Okay, so I think that's the last piece of the puzzle. I can be like type def my int, it's int. So I can use my int just like that. Oh gosh, I got it backwards. I'm so sorry. Type def int my int. Dun dun dun. You can tell I haven't used these in a while. Sorry about this. So it's type def old name, new name, just like that. And then you've made your own type that is an alias for another one. You can just use that in the place of ints. And so that's what C++ is doing. All right. So now you can understand all of this now. That's what pushback is doing. That's what it's returning. Oh man, you could make your own. Okay. Let's see here. And I think I do want to make our own before we leave this. Let's make a simple templated node struct with a templated pushback function. So kind of recreating our lists, but not entirely, because you do have a lab about this. So let's make some templated nodes. Make a struct that's templated. That's no problem. So node, it's a struct node. And it's going to hold t data. And it's going to hold node star next. And it's going to be templated in some class t. And just to get us weaned away from the t, we can use u instead. You can put whatever you want. Okay? It's just the special variable type is called u now. Okay? And then we could make a pushback function. Dun dun dun. How do we want to do this? Pushback. I don't know, to... Or let's do push front. I think that'll be easier. Push font. Push front to whatever the head of the node the list was. So node of t, or node of u, star first, and there'll be a void function, and I don't know, what we can do is we can have it return the new first. And then we're going to give it something that we want to put at the front and be like, I want you to put a new data value of type u. This is a templated. Well, honestly, we could make this one t if we wanted. It's always a variable and it doesn't really matter. How about that? So this function will add a new node t, to the front of a list and return the new front. Alright, so what it needs to do is, well, it needs to make a new node on the heap. Node type T star new node equals new node, and don't get too caught up, it's just another type. Instead of node, it's node T now. New node T, new node data equals data val, the new node's next is the old front. Just review the slides from the list lecture if this is all looking weird to you, but we made our new node, we just got to put it at the front now. So we'll say that new node arrow next equals the old first, and now the new first is our current node, is our new node, the one that we just put at the front. So return that, because I have said that we're going to return the new front. So now we can use this, and it'll just work as long as we start out at first as an empty list. There. So we can be like node of, I don't know, node of ints star first equals null pointer, so initially empty list. And then let's add to it first equals push front first and 3, then 2, then 1. How about that? Alright, so now we'll have 1, 2, 3. We have the list 1, 2, 3, and let's go and print it out. For node of int star n equals first, n is unequal to the null pointer, n equals n arrow next. We'll be like cout n arrow data and a space, and then at the very end we'll be like cout new line. And this should print, assuming we did all this right, 1, 2, 3. Essentially, you know how to do all of this, it's just the new thing is templates. Alright? One, two, three. And of course we can make nodes of strings, of bools. Just immediately, by virtue of using templates, we can have as many different versions of this as there are types. You can make a list of lists, and in fact, you'd be like node with a node star inside. Yeah, that's totally possible. Yeah, so I think that's where I wanna put us there. And just for posterity, let's say that this was push front that we eventually did. Okay. With that, I want to move on to a different data type that you can make out of lists. Okay? It's called the stack. And this is now an overloaded term. So we already know about the runtime stack. The stack ADT, abstract data type, is just a generalization of the runtime stack that we already know. It works in the same way. You can push and pop and do cool stuff. So let's pretend you're washing dishes after a meal. Such a good son or daughter. So here is your stack of dishes, and each family member, as they're finishing their meal, they come and they put another thing on the stack of your dishes, another dish. And you're kind of stuck only ever washing the first one, because it's kind of hard to get to the ones down here, right? You're kind of stuck only ever washing the first one. And we can model this with a stack abstract data type. Isn't that fun? So the operations on a stack are the following: push, pop, top, and empty. And this is essentially what it's about to mean. I'm going to give you a very high-level example of how you implement it in a second as well. So here is our stack. We can model it just like I've been drawing the runtime stack. Let's pretend we have a stack of ints. So originally it's empty, and so empty will return true, the empty method. But we can start putting stuff on a stack with push. And you always, when you push, you add to the top of the stack. So actually, just to save me for later, let's put this over here, and this can be right here. Beautiful. All right, so that's our stack. It's empty right now. I can push to add one thing on it. I'll add 5. Okay? I can push again to add 42. And the top is always the last thing you put on it. Okay? So it's like a stack of dishes. And when you want to take something off, you don't just want to look at it with top. You say pop, which removes the top. So say we had, I don't know, 7. We push that, and now it's, of course, our new top. No. Darn. Erase. Then by popping, we can get rid of it. Okay? So we just popped. Boop, goodbye 7. Now we're back to 42 on top. Okay, and you can keep popping until the stack is empty. Like pop 42, pop 5. Now the stack is empty. And you can't really pop an empty stack. Hopefully that makes sense. Okay. That is the model of a stack. It's really not that bad, and there's some cool stuff that you can do with it. All right, so at a high level, you can implement this using lists. And let me show you how. All right, so let's imagine that you have a list, and you want to represent this stack with a list. 42, 7. You actually have 2 options. You can be like 3, then 7, then 42. Or you can be like 42, then 7, then 3. You know the list operations. How would you do this? What does it mean to push? If I want to add like a 4 here, where would it go? Well, if I'm modeling it like this, it better go at the front. I can push to the front. Now you understand why it's called push. And if I wanted to put it here, like if I wanted to put the 4 here, let me draw. Here it would have to go into the front. I'd be like boop, boop, push front, what? And then here, for this one, it would be push back. You see that? Isn't that beautiful? Let's see how well I can put this down where it needs to go. So you can use a list for this because it's very easy. It's super easy. Because it's super easy to add stuff to them. In any order, in fact. So you have options when you're implementing a stack. You can put it at the front, put it at the back. Hey. Alright, so push is super simple now. If I want to push something to a stack, it'll be just add to either the front or the back. Depending on what you decided. Depending on how you're modeling the list, or how you're modeling the stack. Okay? Either add it to the front or to the back. This is your stack. 42, and you want to push 5. And right now it's 42. Well, maybe you can just add it to the front. Maybe that can be the way you draw your lists. Alright, you can be like 5 is now the new first, and 42 is the next thing. Okay, always push to the front. And so now the top of your stack is always the first element. All right? And if you did opposite, the top of your stack would always be the last element. Not an issue. So that's that. And what's the running time analysis of push? Well, it's either a push back or a push front. Let's just assume it's push front. Well, you remember how much time it took to push to the front of a list? Got to make a new node, set some next pointers around. Oh shoot, that's just a bunch of lines. Just a bunch of straight line code, no loops involved, no nothing. That's constant. Oh man. That's beautiful. That's the world's simplest running time analysis. You're already using this function. It's essentially all you need to do. You're just calling that function inside of another function. It's all constant. Maybe we can make this huge just to demonstrate there's nothing else we need to talk about here. That's why stacks are super nice. They're a nice first data type after we've got a few under our belt. Okay, what about pop? Well, let's pretend we have a list. It looks like this. 1, 2. And assuming we're pushing to the front, always, that means our stack looks like this. And if we want to pop the top off of it, well, I mean, there's already a function that we made, right? We made pop front. You can pop the front of that list. And running time analysis, I don't even need this slide anymore, do we? We'll just be like, O of 1. Because if you're going to get rid of a node, all you need to do is delete it from the heap, change the first pointer, voila. Isn't that beautiful? So you can use a list to implement a stack, and that's beautiful. And then stacks are what's known as a LIFO. I think technically you could also call them philo, probably also works if you reverse them both. What this stands for is last in, first out. So in a sentence, it's like the last thing you put in a stack is the first thing you get out of it. All right, so say your dad was the last person who ate, and he puts the he puts his dish at the very top. You are required to then go and wash that dish. All right, that's your top of your stack. Okay, and I'll give some examples in just a little bit. And yeah, so that's the idea. So stacks are last in, first out. So the very last thing you put on the stack. 4, 2, 42. This is the only thing that you can get through top. Okay, you don't have access. You don't have any other options. We have hidden from the user any way to get below that. These are the 4 things that you can do to a stack. And empty checks if it's empty. Hopefully that makes sense. And so we cannot get here unless we pop. Okay, so that's the idea. And yeah, stacks are first in, first out, or last in, first out. Sorry, thinking of queues. That'll be the next topic in the next set of slides. So stacks are LIFO. Just remember that, last in, first out. And you can model cool things with stacks, and hey, C++ already gave us an implementation of stacks. And I think I would like to maybe give multiple examples. I thought of another cool one. Reverse. A list using a stack. That's a very common operation. So we'll get to that, probably not today. But let's poke around the documentation and get ready to implement stuff using the C++ stack. All right, so it's in containers. And oh man, this is a term that people know about, LIFO. Okay, so I encourage you to read up on all of this stuff. It's very cool. It talks about the underlying container, so you can implement a stack using many different things. You can use a list, you can use a vector. So yeah, it's like all of these options. It could potentially, the standard library could use a vector, it could use a list, It would all work. And it uses one called a deck, and we'll learn about that in a future lecture. All right, so here are the options that a C++ stack in the stack class that was pre-implemented for you has implemented. So you've got a constructor, you've got an empty, check if it's empty, it'll return a bool, get the size of the stack, get the top thing, and it gives you back a reference to it, so you can potentially change the top thing. Push, it's just void, push whatever you want onto it. In place, that's a new thing. We don't really need to talk about it too much. I don't think it'll work essentially the same as push. And pop pops off the stack. Void type, it just does something. And swap, we don't really need to get into right now. Okay, so I think that's all I want to talk about here. It has overloaded some relational operators, so you can check if one stack is less than another for a certain kind of idea of relations. So I'm not entirely sure how it's implementing this, but it's a cool thing. Maybe you can look that up. So that's what the stack gives us, and it's a template, of course. You can have a stack of ints, a stack of strings. You can pick, hey, do I want it to hold everything as a list, as a vector, as a deck? You have options over all of these things. It's so cool. And I think to risk starting early, just to end on a good note, I think I'll stop here. So I'll see you in the next lecture, and we will implement some stuff with the C++ version of stacks. All right, I'll see you next time.